Okay, hey, hi everybody. I'm Iota from Theodoni, from Athens, Greece, and I'd like to thank the organizing committee that invited me to be here. And I'm actually a physicist and doing research in theoretical computational neuroscience. And the past years, I'm studying more seriously philosophy and trying to integrate into my research. Actually, I'm doing a master's in the philosophy department at the University of Athens, where I also did my bachelor's, my physics studies. And before I start, I'd like to acknowledge the people that have contributed to me being here, starting from Manusakis, which are actually a professor in the physics department who has his own theory of consciousness, if you don't know about it. And I see now people are interested more in it. He has a theory where he grounds quantum mechanics on the base of consciousness, which we will listen later today, and similar idea by Chetan Prakash. Manusakis has his own back in 2006. With Gustavo, I did my PhD, and with Nikos and Fanis, and I was 2 years at NYU Philosophy, sponsored by Dave, to study philosophy and taking classes. And now I'm back. Until a few days ago, I'm back to Greece. So the work I will present is something that I've been doing on my own in a self-funded way while I'm looking for a faculty position and hoping that I can find the resource to keep doing it. So we all know that there are different theories of consciousness. Here is a draft sketch I tried to do like 2 years ago, try to understand how different theories of consciousness relate to philosophical frameworks. And but you can also see, when I did that, I didn't know about Signorelli and Seth and Bine, but that's another attempt to classify them. But I'm only putting them here just to stretch that my approach is I want to have a mathematical neural framework of consciousness that it is agnostic to the different theories of consciousness, that it is solely based on experimental evidence coming from experiments that they are done with experimental paradigms for consciousness. And once it replicates the experimental evidence, then we can use it to address predictions from the different theories and see if it can help resolve the different theories. But the question, is it enough to have a neural theory of consciousness? For some people, you might think, yes, we have solved the problem. We have a theory of consciousness, and that's it. For me, it's not. It's just a part of a broader research program that the first time I'm actually presenting it publicly. And so bear with me if it's not that clear, and I would love to have your thoughts. So it's a part of a broader research program, which is on the foundations of intersubjective science, and subsequently in philosophy. So my thesis that, and I think everyone would agree if we actually talk about it, is that science is intersubjective and incomplete, but for now. So I'm really worried about this incompleteness of science, and I will explain what I mean by that. And I'm proposing a way to actually make it complete. So the argumentation goes simply and naively as following, that objectivity actually does not exist, is intersubjectivity. Science we think is based on objectivity, so therefore we know it's based on objectivity. Therefore, science is intersubjective from these two premises. Then subjectivity depends on the brain of the subject. Intersubjectivity is the subjectivity of a group of subjects. Therefore, intersubjectivity depends on the brains of a group of subjects. And therefore, science depends on the brains of a group of subjects. So depending on which subjects do science, the question is, would the science be different? Might be not be different, but we won't know it until we actually test it. For now, we only assume it. So science does not include this intersubjective dependence. So science is incomplete. And then here you have a frustrated physicist that actually wants to have a self-consistent, complete science and to be happy. And therefore, science will be complete when it includes the intersubjective dependence. This is something I hear nobody talking about, and I think is really important, and I call it the problem of closing the loop. What is the problem of closing the loop? For example, we can say a very simple example. Irene is a philosopher of logic and argues about a type of logic as fundamental. But Irene uses logic to argue about her proposed fundamental logic. Is Irene using the same logic she proposes? If Irene had different logic, would she have argued about a different type of logic? Or Aphrodite is a physicist and studies the science of phenomenology. But Aphrodite uses phenomenology to do science. If Aphrodite had different phenomenology, would she have used different science to study phenomenology? So this is this loop that it is, nobody, as far as I know, to the best of my knowledge, is trying to close. And I think it's really important to actually have a complete science in order to reach the full potential of human intelligence. And if we can translate it into mind dependence, maybe animals and other entities or infants, how is to view science from different perspectives, how is to do science from different perspectives. How can we close the problem, how can we solve the problem of closing the loop? What I'm suggesting, proposing, is a new research field, which would be the neuroscience of science. So the idea is that we have two main faculties, phenomenology and reasoning, or else intuition. But most people take intuition and reasoning as a priori, as candid, for example. And I know nobody that cares about this mind dependence of reasoning. Everybody says we are built with that. Yes, but as a computational neuroscience that studies the structure to function relation, I know that the function depends on the structure, and the structure differs across humans, across species, across different agents. So how would be the function on different structures? So we use phenomenology and the reasoning to do science, and the idea is to actually do the neuroscience of science. That means find how phenomenology, reasoning, and discovering the natural laws depend on the brain processes. And I propose we can do that as a starting point, at least with virtual reality, where we are embedded in an environment which we can manipulate the natural laws, the physical properties and the natural laws that govern the environment, and then study how the reasoning about this environment changes systematically as we change the laws of the environment. We can, what I mean, in virtual reality, we can use it to do a scientific study about how the neural dependence of discovering the natural laws, not finding. That's why I put in quote, because my view is that probably natural laws depend on the mind. But what's missing? Many people also think about that in the sense, as we will see later in the talk by Chetan Prakash, that tries to ground science on consciousness, as my professor Manusakis has the grounding quantum mechanics into consciousness. But what is still missing for me is this, part, is once we find the dependencies of the reasoning, phenomenology, of how we find the natural laws, to include them into the science and close the loop. This thing is what is missing. This is what is, for me, in order to have a self-consistent, complete science and a happy physicist that can die happily. And then, okay, so this is the general framework. And in order to do the neuroscience of science, the starting point is to have a neural network for consciousness, let's say as a basis, before we go to reasoning and natural laws and try to define the Newton's law, how it depends on the brain processes. And I do that by studying the conscious perceptual ambiguity, as if you know, with ambiguous figures, a binocular rivalry, where you have, this is a painting of mine for my PhD, because my PhD I did a neural circuit model for binocular rivalry that I will present in a while. And here we have an unchanged stimulus that does not change in time, but can hold two different perceptual interpretations, and your perception switches from one to the other in time, even if the stimulus is unchanged, doesn't change. And this is just my painting, but the most famous is the Necker cube that has been extensively studied, or the phase vase portrait of Rubin. And not only this ambiguity, perceptual ambiguity, is not only the visual domain, but also in other sensory modalities, as auditory, tactile, verbal, olfactory. But I focus in binocular rivalry, which is another paradigm to have the same effect, perceptual ambiguity, when when, for example, if you wear these glasses with green and red filters, and you have an overlap image that they are two images that are sufficiently congruent, you don't see them both, but you see only one at a time. And your perception switches the rivals between these two. You can have the same effect with the Wheatstone, the mirror stereoscope, where you put different images to different eye. And the brain does not merge if they are congruent enough, but sees only one at a time. So Nikos Logothetis, that I collaborated in my PhD as well, did electrophysiological recordings in monkeys with this setup in Binocular Rivalry, where the monkey is presented with two images separately in each eye. And they found that there are neurons in the brain that they correlate with the report. When the monkey says, I see this image, there is a group of neurons that they are active when they say that. Then when they say, I see the other image, another group of neurons is active. So you have two groups of neurons that they compete for perceptual dominance, as it is said. And this is the model I worked in my PhD with Gustavo Deco in Barcelona, which is a local, when I say local, I mean in one area, neural circuit model that captures these dynamics, that has two excitatory population, one, let's say, red neurons that they are selective, they are active when, let's say, the monkey is a red image, and the blue neurons, that the neurons are active when the monkey is a blue image, and then there are non-selective neurons and inhibitor. This is a spiking network. Each neuron is an integrated fire neuron, gives spikes, it has a differential equation, and they are all interconnected. It's like a system of thousands, I don't know, depending on how many neurons you want to have in each population. And what I did is I used this model to study the dynamics, which actually previously had been studied for working memory, attention, decision making, and me by adding spike frequency adaptation, I could capture this rivalry. And I reduced it with a mean field, I did a mean field reduction to a 4-variable firing rate model that is a simplification, but also direct connection to the big spiking network to study these dynamics. And for example, to simulate binocular rivalry, what I do is I stimulate externally, I give current to equally, not to as many bias, to these two populations. And I see the dynamical regime. Here is the synaptic gating variable, let's say, of these neurons, depending on the level of adaptation that exists in each neuron. And there's without stimulation, it's like the firing rate. It is not active, and if there is stimulation equal, you have a dynamical, this is the portrait of the dynamical regimes. So it's a dynamical system where you can have it from a bistability regime to a limit cycle. And I found that you need to be close to the Hopf bifurcation here to capture the statistics of the dynamics of these two neurons. So what I mean the statistics is how long, for example, they perceive one image over the other, and several other properties that they have found with experiments. And this is just to show that with the same parameters of the mean field, if you use the spiking model, you get the same dynamics. That the mean field works well, for example, just to show that you have a good reduced model. But this local circuit, where is it in the brain? Here I don't talk about theories, I don't care. I just care about experimental evidence independent of any theory. Is this area in V1? Is it in V4? When I actually did it, it was in PFC because the data were from PFC. So I assumed, okay, it's from PFC. But could be somewhere else, could be in parietal cortex. There is a big discussion about the locality of which area in the brain is most important, which areas in the brain are most important for consciousness. Or like, is it an inter-areal subnetwork? But which one? And that's a question still unanswered, and different theories have different predictions for that. So what and I say I don't care about the theories, I only see the data. What data? I'm based on a variant of the binocular rivalry, which is the binocular flash suppression, which is extensively used to find the neural correlates of the conscious content in binocular rivalry, which is just that before having the two images, they first saw one of the two. So first there is nothing, they saw one of the two images, so you know that if here you have a neuron that's selective to the green grating. So when you saw the rival image, it doesn't go up. And then when you flash the new image, you have these two in the binocular flash suppression, all the time the flash image will win the perceptual dominance. And then you can use this to have to find the neural correlates. And what they have found is that there is a distributed neural correlates across the cortex, and actually it increases along the hierarchy from V1 to DLPFC. And here I represent it in the macaque cortex. But now the new thing that I'm doing now is a multi-regional neural network model. Obviously, the local circuit I had is not enough. If you see that there are neural correlates across the cortex, there is this question of how different areas interact to give this distributed nature. So I need a multi-regional neural network model, and this is a biologically realistic because I have the macaque, I have 30 areas, and why I have these areas? Because for these areas, I know how they're connected from anatomy, from retrograde tracing. And not only I have from the mesoscale connectome of this network, I have properties, local properties that give heterogeneity, like local recurrent connectivity based on spine count, and the hierarchy based again on retrograde tracing. And in each area, there is this local circuit that I presented before. So it's like an extension from the local circuit to the multi-regional. Again, it's based on a previously working memory. And we had with Dehaene and Wang a similar model for ignition, but that was mainly to capture the it's in bioarchive, you want to check it out, capture the findings from global neural workspace. Here, I don't care about that. I extend directly from working memory, but we can discuss about it later. This is just a control to show that I'm in a good area. We'll skip this because there is no time. To simulate the BFC, I will just, for 1 second, I stimulate only one population in V1, and then for the other second, I stimulate both, also the other. And I expect to have the dynamic something like this, which I find I have a working region in the model, that working point in the sense that my model captures this increase of neural correlates across the hierarchy. And then this is like overall, if I take these 6 areas, I saw that, for example, I reproduce this increase of hierarchy, but the thing is now I don't have 6, I have 30. So I can predict what happens to the other areas. Or I can use this now to stimulate other sensory modalities. For example, I stimulate somatosensory because I have areas across the cortex. I can stimulate auditory. And I can see if I stimulate somatosensory or auditory, the visual areas go down, but the hierarchy maintains. Or I can stimulate PFC and PPT, which is like one of the proposals from the different theories. Say, okay, what if you stimulate selectively? The thing is, with the model, I have full control of my neurons, I have full control of the areas, and I can selectively stimulate. And I see that if I stimulate PFC, the visual areas are down, but the hierarchy maintains. The same for PPT. The interesting things happen. Actually, this is bad news a little bit for recurrent processing theory, because if you stimulate PFC or PPC, the visual goes down. So maybe they are not important, but these visual areas for consciousness, but these are preliminary results and just predictions. I mean, that is not based on any experimental evidence. Just as an extension. After I have a working model, I can use it to make predictions. And then I can predict what happens if you lesion. And the interesting thing is, if you lesion PFC, these are the red ones are the PFC areas. The others disrupts the hierarchy. But if I lesion PPT, also the PFC areas go down. I stimulate V1 while I lesion the areas. And that somehow indicates that maybe parietal cortex is more important for the information flow, at least, though this doesn't say that the subject is not conscious. The experiment must be done to assess that. Okay, so in summary, my thesis is that science is intersubjective by general framework and context, and incomplete for now. It will be complete when we close the loop. So that's the new thing I'm trying to stress and emphasize, that we need to address and work on that. It's the problem of closing the loop, and how that means how can science include the mind dependence. And I propose that we can close the loop with a neuroscience of science research program, find how science depends on the mind and include this dependence into the science, so we close the loop. And we can do that by starting with a neural network model for conscious perception, and I presented to you a biologically realistic network, such network, agnostic to the theories, but it could help resolve the debate in the different theories. Thank you.